today we're going to go ahead and continue to solve real world, or we're going to go ahead and start solving real world application examples. Like I said, we're going to go ahead and focus or just be on simple quadratic equations. We're not going to go too in detail because that would be now bringing physics into math, and I'll leave that for physics and not math. So we're just going to go ahead and learn some given equations about the applications of quadratic equations, okay? Specifically when an item travels a certain distance. So with that said, I'm going to just go over which some quadratic equations and ask you guys a question. How can we use a quadratic equation to solve a real world problem? Now, let me go ahead and show you guys a little video so you guys can have an understanding of where they're located or how do we use them in real life. Believe it or not, they're everywhere. So, like I said, we don't have to identify the initial height versus the last or the final height, nor anything about gravity being involved. It's already being done for us. It's been given through the coefficient right here of 16. So all that work is already done for us. Now, whenever we describe the distance, we're going to go ahead and describe it as that function, the result of the function. So here in this case, DFT is going to be that distance. Now, in this case, T is going to be described as time. So we have our two factors, our two parameters that we're going to go ahead and be looking at that are going to help us identify our beautiful function. We have our distance, DFT, that's our function. What's happening while the time is running, okay? While time is happening. Our coefficient here is 16. And we have our beautiful equation. Now, this is, for example, whenever you're given an initial height and you want to see what time or the duration of the item or the object that you're trying to go through the parabola takes to hit to the floor. Okay, so there's no initial. Sorry, there is an initial. There's no final. The final is automatically 0, so we don't take that in consideration. So let me go ahead and say this. Ready for the next one? There's 2 of them. Let me go ahead and clear. Now this one is basically the same, very similar, but we're going to go ahead and have a next component. This one is our initial height. So very similar to distance, we're not going to describe it as height. And it's going to be considered to be our final height or our height. Our h sub 0 or h sub o, it's going to be considered our initial height. And this formula is going to be used again whenever we're given 2 different heights. So for example, we start at a certain height and we want to know how long it takes for it to get to a different height that it's given from the first one. Okay, so T is still representing time. And we're going to go ahead and use those parameters as well. Okay, so this one is particularly used whenever there's a height included or a different height. An initial height. Okay, ahora sí. ¿Listos? No, we're barely starting. We're barely getting started. Okay, ready to apply all this? Okay. All right. Everybody has this? There you go. We have our height, our initial heights, and our T time. So we're going to go ahead and identify what's unknown and then solve for what we have with what we have. Okay. Listos. Here we go. All right. So here's our first example. It says right here, write and solve an equation to answer the question. Give the exact answer and if irrational, meaning that if it has a square root, go ahead and find the decimal value or decimal value approximation to the nearest 10th of a second. So this one says, if you drop a water balloon, how long does it take to fall 4 feet? So 4 feet, guys, imagine I'm right here. I'm almost, well, I'm 5 feet. 4 feet about right here. So I'll grab it and I just let it go. So how long does it take for me to drop or for it to be from my hand and then hit the floor? About 1 and some change. So let's go ahead and see if it approximates 1. So in this case, we have an initial height. However, our final height is the floor, right? From where it starts all the way to the floor. Now, whenever we have this type of example, we're going to go ahead and use that first equation where we have our distance, DFT equals 16t squared. We already have our beautiful model. We don't have to identify or include any gravity because our coefficients are already done for us. All we have to do is identify the parts that are given. So, for example, DFT is our height or the distance. What's the distance that's given here? 4 feet. What do we have to find? How long does it take? So what does it represent? How long does it take? Time. We need to find what time it takes to travel from 4 feet all the way to the ground. So we have T. We're going to go ahead and write a question mark. What is the time that we need to find? So let's go ahead and substitute our following measurement or our following parameter. Here we have 4 equals 16t squared. Now, the way that we're going to solve this is by doing the square root method. Do you guys remember the square root method? Yay, I hope so. Okay. All right. So we have to isolate this beautiful t. How do we isolate it? Not subtract. It's multiplying. Divide. Go ahead. Divide 16 on both sides. Let's go ahead and simplify on my left side. 1/4 equals t squared. And I have a t squared. What's the inverse of a square? Square root. So let's go ahead and square root both sides. Now, we have t equals the square root of 1/4. You can go ahead and separate your radical to both your numerator and your denominator. So we have square root of 1 over square root of 4. T equals, what's the square root of 1? 1 over beautiful 2. Yes, we consider the plus and minus value since we took the square root, but because we're talking about time, can we ever go back in time? We wish, but we so we're only going to consider the positive value of time. So in this case, it would be our beautiful time would take 1/2 of a second. We should test it out and see if it does. 4 feet. Let it go. And see if it takes half a second to hit the floor. All right. Let's go ahead and try one more, guys. Now, instead of 4 feet, let's go ahead and see how long it takes for it to travel or to fall. Let's do 16 feet. Go ahead and try this one on your own. 16 feet. How long does it take? Let me go ahead and write time. Time question mark. Go ahead and try this one on your own. Let's see if you guys can do this one. So how did you solve for this one? Or what do we know? Our distance is what? 16 feet this time. So once we substitute our values into our beautiful given equation, what should it look like?
16 equals 16t squared.
T squared. Perfect. All right. Now we're going to go ahead and start with inverse operations. What's my first inverse operation? Let's see. Lisha, what's my first inverse operation? Now that we know that we have distance equals 16. So how do we solve for t? What's our first step? If it's multiplying 16, so it would be divide by 16. So let's go ahead and divide by 16. We're left with 6 divided by 16 is 1. So t squared equals 1. What happens next, guys? Square root. Square root. We're left with t equals square root of 1 is beautiful 1. So how long does it take? 1 second. We should test it out and see if it's true. It doubles, yeah. It doubles in time. So the faster, the higher you are, the faster it travels as it's getting closer to the ground. Okay, now let's go ahead and try our next example. Now that we got the essence of the first equation. Now this one's a little bit different. Just because we have different heights. So same idea, write your equation and then solve. Let's go ahead and approximate to the nearest hundredth of a second, or sorry, tenth of a second. So the rooftop of a 5-story building is 50 feet above ground. So we already have our beautiful 50 feet story building. 5-story building at 50 feet. How long does it take the water balloon to drop from the rooftop, pass by the 3rd story window at 24 feet? So notice here in this equation, we have not one, but 2 heights. So this should tell us that we're going to go ahead and use that second equation to determine how long does it take for it to travel from initial heights and then reach a particular height. Now, in this case, my equation is now h of t equals my initial height minus that same part of that first equation that I have now. We're going to go ahead and subtract that time away from it. So we still have a quadratic. It's an initial height. Basically, we're going to go ahead and have a starting point. So we have 3 unknowns this time. We have our height, we have an initial height, and we also have time once again. So what are we looking for? How long does it take? So time, we don't know what it is. Now, our initial height, do we have the starting distance? Yes, we do, 50. And the height that we want to find, or interested in knowing the time, it would be 24. So let's go ahead and substitute all our values. We want to know at what time will it hit 24, starting from 50 feet, and is being directly dropped from our beautiful 50-foot story building. All right, now that we have this, we're going to go ahead and solve like we solved by doing the square root method, basically isolating that beautiful variable. So my first inverse operation should be subtract 50, subtract 50. I'm left with 24 minus 50, negative 26 equals negative 16t squared. My next item is to divide by negative 16, divide by negative 16. I'm left with t squared equals positive 16 over, positive 26 divided by 16. We can go ahead and simplify that as a decimal value. What do you guys have? Yeah.
Positive
1.6. Now my next step is to square root. I'm left with t equals, what is the square root of 1.6? Should be 1.26 or 1.3. And it takes 1.3 seconds to fall from 50 stories all the way to the 24 feet or the 3rd story window. Not too bad, right? Not too bad. Okay. All right. Let's go ahead and try one on our own, guys. Let's see if we can do this one. Let me go ahead and clear. And let's go ahead and do number 3. Now, this one is a little bit different because we're not on the Earth's surface. This time we're on the moon. And we're going to go ahead and assume that we have a different equation that's given to us. So it says on the moon, the distance in d feet that an object falls in time is modeled by the function distance, or d of t, equals 8 over 3 t squared. We're going to go ahead and suppose that the astronaut drops a tool. We want to know how long it takes for it to hit the floor if it was dropped from 4 feet. So let's go ahead and try this one out. We have our distance. This one's a little bit different from the first one that we have. So this one we have d of t equals 8 over 3 t squared, and it's falling again from 4 feet. So we let it go, and it's going to hit that beautiful ground. So try this one out on your own. Let's see what you guys get. Hi, this one. Okay. Now we're given our equation. This time is a little bit different from the first one that it's already given to us. Our coefficient is not 16 anymore, is a little bit lighter since when the moon, we are a little bit lighter. So our gravity is not pulling us down as much as it is here on Earth. So we have 8/3 as our coefficient. And it still has our beautiful trajectory, or that parent function is a parabola. Okay. Now, in this case, we can go ahead and find our d of t from the given information and also our time. So what are we trying to find again? Times. We still don't know what the time is in this case. Now, do we have a height that we're dropping this or this tool being dropped from? 4 feet. So we're going to go ahead and make this equation equal to 4. So 4 equals 8/3 t squared. So let's go ahead and continue with that square root method. Now, notice here that my beautiful coefficient is 8/3. We can go ahead and solve this by either doing the inverse operations. It's multiplying 8 and dividing by 3. So we can either multiply by 3 and then divide by 8 or multiply by the reciprocal. Either way would be the same procedure. So we can go ahead and multiply by 3/8 on one side and multiply by 3/8 on the opposite side. This automatically eliminates those values that we have in front of our beautiful variable. So we have 3 times 4, which is 12. My denominator is automatically 1, and we have 8 times 1 is 8. So we have t squared equals 12/8. Now, what happens here? What's the inverse? Square root. So let's go ahead and square root both sides. Square root, square root. We're left with t equals, we can go ahead and separate if you want to, square root of 12 or square root of 8. Again, you can go ahead and put this in your calculator. If you guys don't have, if you guys have your phones are very different. You have to do the fraction first and then the square root of that fraction, okay? So it would be 1.22 or time equals approximately 1.2 seconds in this case. So again, I can go ahead and show you guys, yes.
Unlike the test, when we do this, we'll get dark points and we don't put the squigglies.
No, because there will be approximately 1.2 and so on and so forth. As long as we're following the nearest 10th rule. And we're approximately according to what's asked. Okay, let me go ahead and give you guys your homework for tonight.